Welcome to the Bayes Server channel. Bayes Server is a powerful tool for building Bayesian networks and causal AI models. In today's tutorial, we're going to be looking at the Bayes Server data sampling feature. We'll be largely following the tutorial that can be found in our Learning Centre, but we'll also delve into the overall help file for data sampling, which has some additional information such as how do these values actually get generated, and there's some more information about things like weights and so on. We'll get into that later. So if you open up Bayes Server, it will typically by default look something like this. To generate samples from a network, we need to use a network that's already been built. So whether you've constructed it or you're using one of our samples, that's fine. But the network needs to have its nodes, links and distribution specified before we can then go ahead and generate samples. So today we're going to be using the waste network, which you can find here. So just single click on that and that will open up our network. Let's just make that a little bit bigger so we can see it a bit more clearly. Now, to start off with, what we're going to do is generate some samples from this network without any evidence set on it. So what I mean by evidence is perhaps household is true, or in builder state is intact, that kind of thing. So we'll start with no evidence set whatsoever. And to generate samples, it's quite simple. We just go to the evidence tab, hit the sampling button here, set whichever options we want. So by default, we've got 100 samples. We'll stick with that for now. And we'll leave the others as defaults. So simply hit the run button. And there are our samples. Let's just make that a little bit clearer. So you can see we've got case 0 through to case 99. So it has indeed generated 100 samples for us, which is great. So from here we could export these to a spreadsheet and we could do some downstream analysis in our favorite tool or in Python, whatever. We can also add it as a data source as if we'd loaded it from a spreadsheet or a database within the Bayes Server application and use it elsewhere. In this next section, we're actually going to look at how these records or cases are generated under the hood. So if you're not interested in the technicalities, feel free to skip this section and move on to the next one. But certainly for me, I'm very interested in how things work under the hood. So if that's of interest, you might want to follow along. And all of this information around how it works can also be found in the standard data sampling help. So not the tutorial itself, but the associated help for just general data sampling. You can see in this section here, how does data sampling work, which is basically what we're going to follow through here. Okay, so we're going to take a slight departure from this waste network. And in this case, we're going to use a slightly simpler network, which is called the Asia network. So click on that. Again, let's make it a little bit bigger so you can see it more clearly. Now this network is slightly simpler in the sense that it's all discrete nodes, and I think when we're explaining how data sampling works, it's going to be quite a bit simpler. So we'll start with that. Okay, so when we're trying to sample from a network, if we're trying to sample from, say, the smoker node here, each node in a Bayesian network has a distribution which is conditional on its parents. So smoker will have a distribution that looks something like this. So you can see it's just smoker is true, 0.5, smoker is false, 0.5. There are no parents here. Whereas if we look at a node that has a parent, say has lung cancer, has the parent smoker, if we look at the distribution, then you can see its definition is at the top here. We now need to specify the probability of has lung cancer given smoker. So it's a little bit more complicated. So if we want to sample from the smoker node, it's actually quite simple. All we really need is a random number generator that perhaps gives us a number linearly between 0 and 1. And then the number that comes back, if it's less than 0.5, we sample smoker equals true. If it's greater than 0.5, we would choose smoker equals false. Or equivalently for visit to Asia, we can do exactly the same thing. In this case, the probabilities look slightly different, but we can again sample a number between 0 and 1. If it's less than 0.01, then we would sample visit to Asia equals true, otherwise false. So it works in the same way. Now, when we get to a node like has lung cancer, the distribution has lung cancer given smoker. So in order to sample from has lung cancer in the way that we did previously, we need to know the value of smoker. But if we've already sampled from smoker before we get to this node, then we know what that value is, and then we can filter this distribution down. Say smoker turned out to be true, we can set it to true, and then we can sample in the normal way from this distribution here, 0.1 and 0.9. Okay, so that's great. So now we know for each node how we can sample from it. However, there's one final piece of information that's important. So how do we know, how do we have an order in which we can sample from each node that guarantees us that we already have sampled from all of its parents? So for example, dyspnea has two parents, tuberculosis or cancer, and has bronchitis. When we sample for dyspnea, we need to make sure we've got values for both of those, i.e. they've been previously sampled. So there's a way we can do this, and it's called a topological sort, which is a standard algorithm for graphs that look like this, i.e. they're directed. We've got arrows, going from one node to another, and they're what's called acyclic. So they don't have any directed cycles. So you can see in this network there is like a cycle here, but it's not a directed cycle. So it's not going back on itself, if you like. So for example, with this Asia network here, a topological sort would look something like this. 1, 2, 3, 4, 5, 6, 7, 8 for each of these nodes. So as long as we sample in that order, we know whenever we get to, say, node 6, that 3 and 4 have been sampled rather. When we get to 8, we know that 6 and 5 had already been sampled. So that kind of solves our problem for us. Okay, so now we've got an idea of how this works under the hood. Let's go back to our waste network and follow on with the standard tutorial. Okay, so we've generated some data here, but what happens if we've got evidence set on some of these nodes here? So if we look at the tutorial, it wants us to set filter state to defect and dust emission to 4.4. Okay, so let's go and do that. So filter state we set to defect simply by clicking on this bar here. So you can see it switches to 100%. And then I think it was dust emission to 4.4. We can set that by clicking in here and typing in the number 4.4. Okay, so now we have some evidence set on this network, but we can still sample from this network. So let's open up the data sampling window again. We'll stick with the default 100 cases, but note that often you want quite a few more cases like that. You might want 10,000 or a million. You might want tens of million. If you're getting to sort of quite large numbers, you might prefer to use the API and dump it out to a database or something. But nonetheless, you can set that value here. Now in this case, we're going to importantly set this use network evidence flag here. So let's turn that on. And we're also going to set a few other options, just like the tutorial. So we're going to set log likelihood to true, weight to true, and log weight to true. So let's go and do that. Okay, so let's quickly run it before we go back and explain what these different options mean. So now we've got different values being generated in each sample here, but you'll notice first of all that dust emission is always 4.4. So if you scroll down, it's always 4.4 because we set it to fixed evidence and we wanted that to come through. And filter state will always be defect as well, which is to be expected. Now we've also got these three additional columns here at the beginning. We've got the log likelihood column, we've got a weight column, and we've also got a log weight column. So let's just try and explain these quickly. So the log likelihood column basically tells us how likely it is that our model could have generated that sample. Now when we've got like 100 or tens of thousands of samples, certainly as you get larger numbers, the data mimics the network, i.e. because the data was generated from the network, the distribution of that data generated should largely match the network itself, particularly as you approach much larger sample counts. Okay, so whether or not we have fixed evidence set for the samples, it can be very useful to output the log likelihood. The log likelihood is just the logged value of the likelihood, and we use log just for computational reasons to avoid things like underflow. But the associated likelihood basically just tells us how likely that case is or how anomalous it is. So what you can do is generate hundreds of thousands of samples and get an idea of the range of likely values, and then when you've got new data coming in that you want to test, you can see how does that look against the standard sort of distribution. Now the weight is very much specific to when we have fixed evidence on there, and it basically tells us how likely the fixed evidence is given the sample that's being generated. So we'll need to explain that in a little bit more detail in a second, but the log weight is again just the logged version of that, and internally we calculate it in such a way that it avoids underflow. So there's information about what this weight means and how important it is, and also how it's calculated in the standard data sampling help you can see here. For those who are interested, we'll briefly touch upon how that works right now, but feel free to skip to the next section if you want to avoid the technical detail. Okay, so again we'll switch back to the Bayesian network here because it's just a little bit simpler, and say we've got some fixed evidence on has bronchitis equals true. Now when we come to sample from this distribution, so we've already know smoker, we've already sampled smoker, and say it came back as true through a random number generation process. Then when we get to has bronchitis, we know that smoker's true, so we could in here filter down to true just to see what our remaining distribution looks like. Now normally without any fixed evidence we'd then once again use that random number generation process to decide whether that value lies less than 0.6 and then we would choose true, otherwise we'd choose false. But in this case we're overriding it, we want it always to be true. So we can simply go and put true in our sample. But because we've sort of overridden the general random generation sampling process, we need to weight our resulting case, and we do that by picking this number here, so the 0.6. So the weight initially for the entire sample is just 1. So if you don't have any fixed evidence, the weight will always be 1 for every case. But here we would multiply that 1 by the 0.6 here, and then for any other nodes that had fixed evidence we would then again multiply it by the corresponding values, and that's how you generate the weight. And just a final remark on that weight, because we want our samples to reflect the same overall distribution as our original network, such that if we wanted to we could generate 10,000 or 1,000,000 samples and delete all the distributions in our network and relearn those distributions using our sample data, and what you'll find is they'll be very similar particularly if you've got lots of cases. We're going to do that same learning process, or put your sample data into a downstream app or some Python code or whatever. You need to include that weight, otherwise the samples are not representative of the distribution anymore, and if you were to relearn your network it wouldn't be the same. So touching upon weight there, but just to be clear, if you've got fixed evidence then always output the weight, and in fact the user interface will warn you if you don't. If you haven't got any fixed evidence you don't need to worry about weight at all. Okay, so finally let's look at generating some sample data with missing data. So we've currently got switch back to the waste network here. As you can see, we've still got some evidence set on here. So let's go to the evidence tab and click clear. That will get rid of all that evidence. And then once again, let's hit this sampling button here. So we can leave it for the defaults of 100, but now we want to generate some missing data in our output. So if we expand this show 9 more items section, what we can do is set the missing data probability to a value between 0 and 1. 0 the default being no missing data, 1 being 100%, so which would be a bit weird, but let's try 0.1, as in we want 10% of our data to be random. And again, let's just run this to see what the output looks like. So you can see in this case, there's roughly 10% of these values now have null or missing data in them, which can be useful for a number of different reasons. Now, if we want to be a bit more specific about this, we could click this missing data exclusions, and you can say, okay, well, I don't want these ones to have any missing data at all, and so on, which is quite useful. Okay, so let's just switch back to the tutorial. I think we have pretty much completed it. Thanks for watching. There are many other tutorials available on our website, and if you're interested in particularly video content, then please do take the time to subscribe, as we are planning on lots more content like this. Thanks again, and goodbye.